Hello everybody, welcome to another video lesson. Today we're getting an introduction on vectors, okay? After this lesson, we'll be able to represent and add with vectors geometrically. Okay, so let's hop right into it with this concept. First of all, what are vectors? You may have seen vectors in another math class or say in physics, but let's go ahead and take a look at the definition again for just the sake of our videos. Okay, previously we have been working with scalars, right? We've been working with an amount of money, right? Or a certain speed, okay? And that just indicates a magnitude or a size, right? But with vectors, we have that same magnitude, but we also have a direction included, okay? So you'll see a vector looking like this when it's drawn out, okay? We have a couple things to point out. We've got our initial point, which we will call the tail a lot of the time. And then we have our direction. We can see it's denoted by this arrow. And then we have our terminal point or the tip of the vector, okay? And you'll see how we write out, how we represent a vector, say when we're working with the equations. It's going to be A, B, say, so A, B is our the initial and terminal points here, and we've got this little kind of half arrow over the top. Or you might see the name of the vector with our half arrow, or you may just see a bold, I try to do bold letters here, a bold name right here. So we've got vector D, and we might denote it with a bold D right there, all right? Okay, let's also have a look at the definition for magnitude. Okay, magnitude for our vectors are the distance between our initial and terminal points of that vector. Okay, so the distance between A and B here, right, that would be our magnitude, okay, for the vector. And that's going to be denoted by, it kind of looks like the absolute value here, kind of looks like absolute value of D, but with our vectors, that's denoting our magnitude, okay? I'm going to throw up a few vectors here because I want to go over a few definitions. Okay, first one being parallel vectors. Parallel vectors have the same or opposite direction, all right? So notice vectors A and B here. Okay, if you kind of cut off the arrows on them, right, they would look like just parallel lines, right? Meaning they have the same they have the same sort of angle, right? But when we add the direction here, we can see that they're going opposite ways. Okay, they're going 180 degrees opposite directions. Okay, but that angle is the same. Okay, and it's going to be denoted by these two parallel lines in between the names of the vectors. So we can see here that A is parallel to vector B, which is parallel to vector C over here. All right. Okay, now we're going to take a look at equivalent vectors. Equivalent vectors have the same magnitude and direction. Okay, same magnitude and direction. So A is equivalent to C, and you'll just see A equals C when we write that out. All right, but A is not equal to or not equivalent to vector B, all right, because they have different magnitudes here, okay, different magnitudes. All right, and then opposite vectors here, same magnitude, opposite direction. Okay, so E and F are going to be opposite vectors, and you'll see it looks like we just have a negative sign out in front when we write that out. Okay, so E is opposite of vector F here. You can see by this little minus sign, right? Okay, let's go into the concept of resultants now, all right? The resultant is the vector that we get when we add two or more vectors together, okay? And we have two methods of finding resultants. The first one is called tip-to-tail method, otherwise known as our triangle method. Okay, so if I were to add vectors A and B, I would just take the tip of vector A here, all right? And I would align that with the tail of vector B, okay? So I'm not changing anything with the magnitude or direction. I'm just moving those vectors. So the tip of the first one is aligned with the tail of the second one. Okay, and now I got to think, what is the exposed tip, or sorry, what is the exposed initial point here? Okay, well right here I have the exposed initial point for A. Okay, and then now I have, what is the exposed end point or terminal point? Well, the exposed terminal point here is going to be the terminal point for B. Okay, so that is going to be how I draw my resultant, starting with the initial point and ending with the terminal point. Okay, So it's going to be the tip of A to the tail of A to the tip of B. Okay, and another method here we have is called the tail-to-tail method, also known as the parallelogram method. Okay, so to do this, we're going to take the tails and we're going to align them. Again, not messing with the magnitude or angle of these, the direction of our vectors. And then we're going to draw in a couple more reference vectors here. And you can see it creates this sort of parallelogram of vectors, all right? And to find our resultant vector, we would just go on the diagonal of this parallelogram here. So starting with the tails that we aligned and going to the terminal points of our reference vectors, that would be the diagonal that we would go on and find the resultant vector. Okay, so you can use either one of these methods. I like using tip to tail. It seems a bit easier, and especially when we get into more than two vectors, it's going to be a lot easier to use. Okay? So let's get into some examples here. First thing we need to practice is just identifying whether we're working with scalars or vectors. So our first example here, we have a car traveling 60 miles per hour, 15 degrees east of south, okay? East of south, so we have a magnitude here, that's our 60 miles per hour. And second, we do have a direction, right? 15 degrees east of south. So that checks both of our check marks or our check boxes, right, for vectors. Okay, so we know that we have a vector quantity here. Okay, second example, we have a child pulling a sled with a force of 40 newtons. All right, so we have a magnitude, right? We've got 40 newtons, but do we have a direction here? We don't know where this child is pulling the sled, which direction, we don't know that. That only checks one of our boxes, so we're working with a scalar quantity here. Okay, let's work on drawing our arrow diagrams, all right, for the vectors that are described here, okay? So vector t is equal to 20 feet per second at a bearing of 065 degrees, all right? And I'll explain what that's not a typo, that 065 here. We're going to explain what that is here in a bit. Okay, what we're going to need here, though, is a ruler and a protractor, all right? So you will need that for our vectors unit. Okay, and I've got, instead of having an XY axis, because I'm working with bearings, I'm going to have a northeast, southwest direction axes sort of lines here, okay? So I'm going to go ahead and get my protractor out, and you notice I've got my protractor aligned with this north-south line, okay? And that's because we're working with a true bearing, okay? A true bearing is a bearing that starts on our north line, okay, and it goes clockwise, okay, from north. All right, so starting north and we're working this way clockwise. Okay, that's our true bearing, and that is denoted, you know you're working with a true bearing when you see the 0 out in front of your angle. Okay, that angle denotes a true bearing, all right? So we're gonna go 65 degrees clockwise from north here, and we'll find that we have this vector t here, all right? Okay, now let's say I drew that with a magnitude of 2 inches. Okay, this scale that we have to include here in our diagram, I've got 2 inches, but the total magnitude of t is 20 feet per second. Okay, so we would divide 20. Let's see. We would divide 20, that's our total magnitude, divided by our 2. Okay, and that lets us know that for every inch of this vector, that represents 10 feet per second. Okay, so that's what it means when it says include a scale in our diagram. All right? Okay, let's look at our second example. M is 60 pounds of force at 80 degrees to the horizontal. So now I am working with X and Y, all right, my X and Y axes. Okay, and we're going to go 80 degrees to the horizontal. Okay, so you would again use your protractor for this. And rotate that up 80 degrees from your x-axis, your horizontal, right? And then you want to go counterclockwise with that, right? Counterclockwise is our standard rotation for angles from our x-axis. All right, and then let's say I wrote this or I drew this with a magnitude of 3 centimeters, okay, or length of 3 centimeters. So my total magnitude here is 60 pounds of force. So I would need to say, okay, 60 pounds divided by these 3 centimeters. That means that for every centimeter on this vector here, that represents 20 pounds of force, okay? Okay, I'm going to work on a couple more of these because I want you guys to get used, especially to these bearings. All right, this bearing is kind of an interesting concept that might not come naturally to everyone. Okay, so we've got vector u is 15 meters per hour at a bearing of, okay, we would say 25 degrees east of south. That's how we would read this. Okay, 25 degrees east of south. So again, we're going to use our northeast southwest bearing lines here. And we're going to start with our vector heading south. Okay, start with it heading south, this first direction. Okay, and then I'm going to rotate from south 25 degrees in the east direction. So in this case, we'd be going counterclockwise. Okay, and what this is called when you see this type of bearing, this is called a quadrant bearing. Okay, the quadrant bearing just starts either on the north line or the south line. And a quadrant bearing is between 0 and 90 degrees. Okay, between 0 and 90 degrees to 90 degrees. And that is just going to land us in one of our quadrants here always. And so you can see if this is 25 degrees, then our true bearing, right, would be this angle here, which would be 180 degrees minus that 25 degrees. That would be our true bearing, okay, if you were asked to represent this in a true bearing, say. So let's say I drew this with a length of 5 centimeters. Again, to include our scale in our diagram, divide that by 5, or divide our 15 by 5. And we get that for every 1 centimeter, that is representing 3 meters per hour for our scale. Okay, last one for our geometric representations. M is 50 feet per second at a bearing of 85 degrees west of north. 85 degrees west of north. So I know that I'm going to start with the vector that's pointing north, and then I'm going to rotate that towards the west. Okay, so again, counterclockwise in this instance, 85 degrees, and that's going to be the direction of our vector here. Okay. Let's say I drew this with a magnitude of 2 inches, then I would have to divide 50 by 2 to find my scale of 1 inch, representing 25 feet per second. Okay. Let's take a look at some vector resultants now. So we're going to be adding vectors here. So if I've got v and w here, and I'm trying to find v plus w, that's what we're going for. Okay, all I would do is we're going to go tip to tail on this one, and then we can find our resultant, again, going from the tail of the first one to the tip of the exposed tip, the exposed terminal point that we have when we go tip to tail here, and that's going to be my vector w plus vector v here. Okay, so now I can bring in my xy axis because we're asked to represent the direction relative to the horizontal. Okay, so this is where you need your protractor. Bring in your protractor, align that with your horizontal. Okay, we can see that we're going 65 degrees here from the horizontal. And then you can bring out your ruler then and say, because we're also asked to state the magnitude here. Okay, so bring out your ruler and see the length of this. So I'm going to say this is about 9.5 centimeters. And so that would be our magnitude of w plus v. Okay. Okay, now over here, I want to take a look at vector v minus w. Okay, now when we do that, I want you to think of it as vector v plus the opposite of vector w. Okay, so the opposite of vector w, oh sorry, I forgot to put our final answer here for this one, but the opposite for vector w, going to be just flipping it, okay, 100 degrees in the opposite direction. It's just going the opposite direction again. Okay, so this is the same thing as adding opposite of w here. Okay, so now I can just do the same thing. We're going to go tip to tail here, and this is vector opposite w that you see here. Okay, and then our resultant is going to be v minus w. Okay, again, I can bring out my ruler, see how long this is, my resultant vector. Looks like it's about 4 centimeters. And then if we wanted to see the direction as well, you would have to put this on your, let's say, x and y axes. And let's say this had an angle, I don't know, we'll call that 5 degrees, okay? So that would be your direction relative to the horizontal for that one, okay? Now let's look at resultants when we have more than two vectors, okay? So we're going to find A plus B plus C here, okay? So we're just going to write in order, all right? So we're going to start with A, and then we're just going to go tip to tail with B, okay? So I'll take B, align the tip to the tail of B, and then again, we're going to go tip to tail from B to C, okay? So from B to C looks like that. All right, and then now, okay, what is my initial point? That's going to be here, this initial point for A. And my terminal point is going to be this terminal point here for C. So that is going to be my resultant vector there. Okay, so that's how we find resultant vectors of more than one vector, okay? Okay, again, I've got A, B, and C, but this time we're going to find A minus B plus C, okay? So again, like on the previous example, we are going to think of this as A plus opposite B plus C. Okay, so opposite B again is going to be same magnitude, just going in the opposite direction. Okay, so now I start with A, again, just working from left to right. Now I'm going to go tip to tail with opposite of B, which we have here. And then I can add C, again, just going tip to tail. Now my resultant here is going to be what's my initial point, that's right here. And my terminal point is right here, the terminal point of C. So this is going to be my resultant vector here, okay? And if you were asked for the magnitude and direction, then you would pull out your protractor and your ruler and give that a measure on both of those to find the angle, the direction, as well as the magnitude, okay? So that's all we have for this video, guys. That's our introduction to vectors. Good luck with your practice.